We're going to talk about the derivative today, which is a mathematical operation that you need to know how to do in order to solve some of the physics problems we're going to be doing. I think that most of you have already done this. So this is basically a review. But I think there are a couple of people who were in advanced math last year, and maybe they're in Calc AB this year, and they really haven't done this yet. So this is going to be a crash course for you. I want you to get help from your peers on this. On the exam, I do have a derivative that I'm going to have you take, but it's going to be a very, very simple derivative. I mean, if you've already had calculus, it'll be like baby stuff to you, okay? So let's say that, now, and I'm also going to take a different approach than most math teachers would, kind of a physicsy approach. So let's get started. Let's suppose somebody's walking along a sidewalk at a fairly rapid pace. Okay, so here's the sidewalk. And let's say they're going to start right here, so we'll make that the origin. And maybe they'll start at the origin. And so here's our person, and they're gonna walk, walk down the street. And let's say that their velocity, we'll keep it at a constant velocity for right now. Their velocity is 2 meters per second. So if 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 2, 4, 6, 8, 10. Okay, so so they're walking along. So now it's kind of hard to draw a person every second here, right? Here's my little person, and I draw pretty good little cartoon dudes, but it's a lot of work to do that. And in physics, we quite often make things simpler for ourselves by just saying, hey, we're just going to pretend this person is a particle. So at 1 second, instead of drawing them like this, I'm just going to put a dot. So there, I've just reduced that person to a dot. In fact, we call it a particle. And a particle is a point in space. All right? But of course, nobody can be reduced to a point in space, but we pretend like it is because it's okay for what we're doing here. And so every second, so maybe we start here at t equals 0 seconds, and there's there, and here, and here. Okay, and so this is where the person is. So we're going to call this x in meters, and this will be t equals 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Let's do it for 5 seconds. And then we're going to, of course, in physics, we always overanalyze the obvious, right? So we're going to graph this thing. And so here's time, and I went 5 seconds, so I'll just go 1, 2, 3, 4, 5. And then I'll do position here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to call position x in meters. And so if I plot this, so I didn't make those increments very well, but we went ahead just to make things simple, start at the origin. And then at 1 second, we're at 2, 4, 6, 8, and 10. So this is a very simple situation. Here a person is just walking along the sidewalk at a constant pace. I mean, 2 meters per second. If you see me walking around campus and I walk pretty fast, I walk about, when I'm walking in my cruising, I got a place to go speed, it's about 2 meters per second. I take, one of my strides is about 1 meter, and I take about 2 strides per second. So it's a very fast walk. It's about 2 meters per second. So if we graph this, you get a nice straight line, okay? And what we said yesterday is that the slope of this line is the rate at which I'm changing position. So you just draw a little triangle, little slope triangle, and you say delta t, okay, 2 to 4 seconds, that's delta t is 2 seconds. And this, here we went from 4 to 8, so that's 4 meters. So the slope is 4 meters over 2 seconds. So that's 2 meters per second. Now, what I've just done here is I've taken the derivative of this graph. Because what is a derivative? A derivative for what we're going to do. Okay, and it's not true for every mathematical situation you're going to get, but everything you're going to do in here, think of the derivative as a function that describes the slope of another function. That's all it is. It's a function that describes the slope of another function. So, and we've said that the slope of this, we've called this velocity. The rate at which I change my position is called velocity. All right, this is what we talked about last time. Well, I'm going to graph it. Why? Because I love graphs. Okay, they're my life. So we said that the derivative of position is a function of time. We call it velocity. Okay, and so this is going to be my velocity, and it's just going to be 1, 2, 1, 2, and this is going to be in meters per second, and 1, 2, 3, 4, 5, and this is time in seconds here. So what is the velocity at, let's see, 1, 2, 3, 4, 5 seconds? What's the velocity? What's my starting velocity? 2. What is my velocity at 1 second? 2. And 2. And at 3 seconds, 2. And at 4 seconds, 2. And I guess at 5 seconds, it's probably 2. So what we have here is a horizontal line. So here we have a function. This is a function, isn't it? Not a very exciting function, but it is the derivative of this function right here. This function describes the slope of this function. Now let's write a mathematical model for this. Okay, here x is equal to 2 meters per second. That's the slope times time plus, and where did I start? Well, I started at 0. So the starting position is 0, so I'm just going to leave it off my mathematical model. Well, what's the mathematical model for this line right here? Yeah, velocity is equal to 2 meters per second. So notice here, look what I've got. I got velocity is 2 times time, 2 meters per second times time. Then the slope of this is 2. So notice that I kept this and it came down here. Okay, now that's going to be kind of something that we're going to deal with. Now, you can extend this to a more complicated kind of situation. What if my position as a function of time graph looked like this? And now, just to make things go a little faster, I'm not going to put numbers on it. I'm not going to put numbers on it because it takes too much time. Let's say here's my position as a function of time. And maybe it looks something like this. So I'm moving away. I'm going to start at the origin. I'm going to move away from the origin at a constant pace. And then I'm going to stop for a period of time. And then I'm going to turn around and go back to where I started. So this is my position as a function of time. Now, remember that we're marching up and down this x-axis, but we're spreading it out over time. So the person is just walking up and down one-dimensional spaces. This person is not walking like this and then walking over here and then walking over here. No, because remember, this is a time axis. What the person is doing is if you start your stopwatch, they would go like that, okay? So they're marching away, stopping for a while, and then coming back at a slower speed. But we're spreading out that motion, over time, okay? Well, what would the derivative of this look like? The derivative is a function that describes the slope of another function. And we're going to say that's velocity, and this is time. Well, what's the slope of this? Well, it's constant, isn't it? Well, look, let's do this. Now, this is called, by the way, a kinematic stack. We're going to be studying kinematics, which is basically the study of the description of motion. We're going to be describing how things move through time and space. And that's called kinematics. And when you put a position versus time graph, and then right underneath it, you have a velocity versus time graph, but the time scale is the same. It's called the kinematic stack, and it's a great way of understanding, trying to understand what's going on. So what's happening here? Well, your velocity is positive, and it's pretty steep. So that means it's pretty high velocity. The magnitude is pretty good. Now we instantaneously stop. Okay, now look, we're going to pretend that that's possible. If I actually tried to instantaneously go from like 3 meters per second to 0 meters per second with no time going by, I'm going to shatter every bone in my body, okay? This is what people try to do when they hit the ground after jumping out of an airplane. They try to it's going to hurt. So please know that these corners in reality are actually rounded a little bit. It takes a little time to slow your velocity down. But we're going to pretend like that's no big deal. And that's okay for now. Then from here to here, what's my velocity? Well, what's my slope? What is the slope over here? 0. So you just kind of darken that in. Now what's the slope over here? It's a negative slope, so that just indicates the direction of motion. The direction of motion is down instead of up. And it looks to me like this is a little bit steeper than this, so it'll look like that. So in my explanation of what a derivative is, this function, and this is a piecewise function, isn't it? Remember you studied that in little pieces. Now, by the way, they really wouldn't be piecewise in reality. You would have a very sharp slope that comes down like this. But let's just pretend like this is okay. This function is the derivative of this function. This function describes the slope of this function. Now I can extend this to a curve, okay? Here's position and time, and then I'll put velocity here. And I'm going to have some negative velocities, that's why I'm putting time in the middle here. So what if my position started here? And you had this curvy motion. So what's really happening here? You have a person who's moving this way on the x-axis and then instantaneously stops and changes direction and moves back this way, then slows down comes to a stop right here, and then moves back a little bit. Does that make sense? So the person is just walking back and forth on this x-axis, and we're spreading that motion out over time. Well, what is the derivative of this? Well, in other words, what's a function that describes the slope of this? Well, for one thing, here's something that's kind of interesting. We don't really care where this starts. Because let's say I drew the same shape, but I shifted it up like this. Well, I tried to draw it so that this has the same slopes as this, right? So its derivative would be the same. These two graphs that I tried to draw it so that this and this would have the same derivative. Okay. Well, let's just qualitatively draw it. What's the slope doing right here? It's negative, right? It's a negative slope. Do you see that? Here's what you can do. You take your pencil and just make a tangent line right there. Negative. And then, see right here, it's 0, huh? The velocity is 0. So that's kind of important. So I'm going to draw a little dashed line that comes down like that. And this is, hey, we know the velocity right there is 0. And then it's going to come up, and then it's going to be 0 again right here. Whenever your object changes direction, that's when your velocity is 0. So I know the velocity is 0 right here and here. But here the velocity started off being negative velocity, and it gradually, fairly steadily changed right here. So it's going to go something like this. It doesn't have to be a straight line, but it looks like it would be. And then it's going to, now the slope is increasing till about right there. What happens right here to my slope? It might be a little bit constant, but looks to me like it starts decreasing to 0. We have a name for that where the slope changes from increasing to decreasing. It's called a point of inflection, yeah. I think my math is a little old, okay, kind of like me. So I'm going to draw another dashed line. And so it kind of increases. And then someone said, look, right in here, it's almost a constant slope. So maybe we'll kind of give it a little constant. And then what does it do? It kind of goes back to 0. And then what happens to the slope here? It becomes negative. All right? So look what I did. This is qualitative. I haven't done any math. I haven't done any limits. I haven't done any delta x over delta t as delta x, delta t approaches 0, blah, blah, blah. I've just qualitatively, this function here is the derivative of this function. That is, this function describes what's happening to the slope of this function. So just keep that in mind. That's what a derivative is. This guy describes what's happening to the slope of this guy. That's why they call it a derivative. This is derived from, this function here is derived from this. It's derived by looking at the slope. Okay? Is that good? All right. And by the way, when I took calculus, I could take derivatives, but I never really understood what they were doing until I took a physics class. So, maybe this perspective is helping you a little bit. Especially, it will. If you're taking calculus for the first time this year, it'll really help. Okay. Well, that's all fine and dandy. These are nice qualitative meaning there's no numbers. These are nice qualitative graphs, but we need to derive some functions. I mean, we need to do it analytically. Very good. Thank you very much. There you go. So let's go back to my straight line over here, right here. Now, how did I find how did I find this derivative? Well, I say, well, what's the slope? Now, the slope here is a constant, but what did I do to find the slope? Well, we know that the slope is equal to the rise over the run. In this case, delta x over delta t. Okay. Now, if it's a straight line, it doesn't matter where you pick your 2 points. If I made this the point and this the point, it would have the same ratio of rise over run. Makes sense. And if you have a piecewise function like this, you can do it, you can just find, okay, well, I just need to find the slope of this, delta x over delta t, that's easy. The slope of this is 0. Delta x over delta t, just pick 2 points on here. It's a straight line, and I'll get the value for this. That's cool. I can do it. But what about this guy? What about a curved function? Okay. Well, that's a little bit harder. So here's what we're going to do. And we mentioned this yesterday. If you have, like this is x and this is t, if it's a curve and you say, okay, I want to know what is the velocity at this, what's the velocity here? Well, I need to know what the slope is right here. Okay, so this is all about finding the slope at a location in space right on the line right here. And we have a trick for doing it. It's called taking a limit. And if you've never done it before, it's pretty mind-bending. It's mind-bending anyway. I've been doing it for 35 years, and it's still mind-bending. So here's what we're going to do. We can't find the slope of this line yet. So what we're going to do, I'm going to call this is going to be t. And this right over here, I'm going to put another point right here. And I'm going to call, from here to here, we're going to call that delta t. We're going to add, here's my time t. I'm going to add a little interval of time to it, and I'm going to call it delta t. So what time is this? Well, it's this time plus delta t, right? Okay. And so we're just going to call this right here. This is x at times t. And then this right here, what is this? This is x at t plus delta t. So this, in the parentheses, this just, let me zoom in, because if you're in the back, you can't see that, I'm sure. There we go. Now that's how I see without my glasses. And now I've got my glasses on. All right, so what we're going to do is we're going to find the slope of this line that connects these 2 points right here. And that'll be an average velocity. And so the velocity here is going to be the slope of this line, which is, you know, delta x over delta t. And so this is going to be, well, what is delta? Delta means final minus initial. So it's the final position. Thank you. Thank you. Oh, that's right, because I zoomed out so much. I mean, I zoomed in. So this is x final. What is x final? X t plus delta t minus x initial, which is just x at time t. Okay? So this is my rise. You know, this is, if I draw a little slope triangle right here, this is x at t plus delta t, this is x at t. Yeah, we're using x's for the rise, that's okay, right? And so there's my rise, and here's my run. Well, what is my run? It's t final, t plus delta t. That's my final time, minus my initial time, which is t, correct? Now this is kind of nice. What goes away? Yeah, the t. So because this is just delta t. Well, duh, okay. So this is delta x over delta t. Okay, so my velocity is going to be equal to, let's just rewrite it, x at t plus delta t minus x at time t over delta t. Now, this gives me the slope of this line right here. But what I want is the slope of this line right here. Well, what I do, and this is just the magic of the limit, is I'm going to let delta t become so small, I'm going to shrink delta t so that these 2 points here and here basically shrink to the same point. And when I allow that to happen, I get a ratio of delta x over delta t that gives us the instantaneous velocity or the actual slope of the tangent line. So let delta t shrink to become super, super, super tiny, infinitely tiny, an infinitesimal. Now, if I blow this up, here's one way of looking at it. Let's look at this right under a microscope, okay, a pretend microscope. Okay. Notice that here's my curve, but when my curve is right there, if you make any curved line, if you magnify it enough, what does it look like when you magnify it a lot? It'll start looking like a straight line. So when I look at this, so here's my here's my 2 points, right? And so here's my delta x and here's my delta t. They become extremely tiny as I let delta t shrink to 0. And I have a way of writing that down. I'm going to say, let's take the limit as delta t goes to 0. Now this guy right here, all it is doing is saying, hey, we're going to let this guy get really, really close to 0. Is it going to be equal to 0? No. Why? Because you cannot divide by 0. Okay, the mathematical gods will have their vengeance upon you if you try to divide by 0. But you can divide by something that's approaching 0 as long as, and it's going to be fine. Because as delta t is getting tiny, what's happening to delta x? It's also getting very, 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 very tiny. Is it okay to divide tiny by tiny? Yes, watch. I'm going to divide tiny by tiny. What if delta x, here's delta x over delta t. What if this turns out to be 0.00000000000000000000000. Am I off screen? Nope, not quite. 1. Okay, this is like, okay, we're talking like the width of an atom here, okay? Meters. Divided by 0.00000000000000002 seconds. Now what is this equal to? It's equal to, 0.5 meters per second. Is that okay? Yes, that's legal. The mathematical gods are satisfied. So what we're going to do is we're going to let this shrink to something really that's approaching 0, but like, well, that looks like it's approaching 0. If you gave me this much money, I would be unhappy. Okay, because that's pretty much 0 money. All right, so we have this little operator here. It's called the limit, and you just do it. You just plug your values in to your function into this, and this is really the definition of the derivative. I'm doing it in under the context of velocity, but instantaneous velocity, by definition, is the limit as delta t goes to 0 of x at t plus delta t minus x at t divided by delta t. And this is what you do. and it's horrible to use. Well, let's do the problem that we've already solved and apply this guy to it. Here we have where we started this lecture with this function right here. So we're going to use x equals 2 meters per second times time, and we're going to take the derivative of it, okay, using this limit here. So here's my first example problem. X of t equals 2 meters per second times t. So what does so the velocity therefore is going to be equal to, well, just take a look at this, just do it. Wherever you see this, put the function x at t plus delta t. So it's going to be 2 times what? Well, let me put meters per second in there. T plus delta t. Don't freak out. It's just, what is the function saying? Hey, wherever there's a time, just put time plus delta t. Minus, what's my function? X of t, which is, x of t is just 2 meters per second times time. Over delta t, and like I limit as delta t goes to 0. Now you just do it. It's just like simple arithmetic after this. V equals, well, I'm going to multiply 2 in there, so you get 2 meters per second times time plus 2 meters per second times delta t minus 2 meters per second times time all over delta t, and the limit as delta t goes to 0. I always forget to do that. All right. Now, this is sweet, because what goes away on the top? Yeah, this and this go away. That will always happen. Boom. And then, so the only term left on the top is this guy. And then I divide by delta t. What happens? Cancels out. Boom. What's my answer? Victory! It's 2 meters per second. No, I already knew that. So why did I go through all of this? Well, because this illustrates the procedure with a simple problem. But what if I gave you a function that was a little more complicated? What if I gave you a function like this? Um, 2t squared plus 1. Okay, we'll do it. Let's do it. Okay, so v is equal to the limit as delta t goes to 0. Well, wherever there's a t, put a t plus delta t. So this is going to be 2 times what? T plus delta t squared plus 1. Minus, so there's this is my x final, minus x initial. Well, what is x initial? It's just 2t squared plus 1. Got to put the parentheses in there. Divide all that by delta t. Okay? Now, is this is a little harder, because you got to square this thing, and it's getting messy, but we'll do it. V is equal to the limit as delta t goes to 0 of, all right, well, you've got 2 times t squared plus 2t delta t plus 1, right? Minus 2t squared minus 1. I just got rid of that. Did I do that right? Oh, plus delta t squared. Why did I plus 1? Oh, okay, plus. That's what happens when I go to this. All right, plus delta t squared. Thank you very much. That's important. Plus 1. And there, this is this thing expanded out. Minus 2t squared minus 1. You got to remember to distribute that negative in there. All over delta t. Okay, so what do we got to do? I got to distribute that 2 in there and get rid of all the parentheses. So I'm going to go 2t squared plus 4t delta t plus 2 delta t squared. Did I do that right? Yeah. Plus 1. Help me out here because I always mess this stuff up. 2t squared minus 1 over delta t. Oh, dang it. Right, there you go. Now, what goes away? Stuff will go away. The original function always goes away because you got a 2t squared here, you got a minus 2t squared, so it goes away. That will always happen. The original function had a 1. Oh, there's a minus 1. So they go away. Now I got this stuff left over. I've got the delta t in there. So the delta t will cancel with that one, and it will cancel out the delta t squared, leaving a delta t behind. So v equals the limit as delta t goes to 0 of 4t plus 2 delta t. Now that's almost, we're almost to my answer, but what's this delta t happening to it? It's going to 0. So 2 times something that's going to 0 is still going to 0. So this thing goes to 0. The only thing left is 4t, and that's my velocity. That's my derivative. This is called dx dt. Is 4t. Now, I'm done doing limits. Okay? Limits are horrible. Look how much work it took to do this simple little thing. Okay, well, what if I gave you this? All right, I'm going to give you a function to do. Okay, I want you to take the limit of that. No, I don't. I don't. If you had to take t plus delta t to the 5th and put that in the same expression, t plus delta t to the 3rd, to the 2nd, okay, it will take you all day. You could probably do it algebraically if you don't make any mistakes. No, you're going to make mistakes. It would take you probably a week to get it right, to fix all your mistakes. This is ridiculous. But if you know the trick, and most of you know the trick, right? V is equal to 25t to the 4th plus 6t to the 2nd plus 18t minus 4. Done. That's a lot easier. Because what we do, look, the derivative is defined by the limit, okay? This is the, where did I put it? This is really the definition. Now, I mean, I applied t for time and x for position, so this is specifically for velocity, right? Instantaneous velocity. But really, if you just don't worry about the variables, what they mean, this is the definition for derivatives, the slope. Okay, but it's ridiculous to use for really hard problems. So what mathematicians have done is they have given us a set of rules, of shortcuts, where it really is doing this, but we don't have to do this. Okay, and those rules are in your book. And they are right here. This is the appendix of your book. Let me show you. Let's see. Let me focus. Let me zoom in and focus. Okay. If you know these, you'll know everything you'll need to know for AP Physics. You know these, how to use these rules. Okay. Now, here, A is a constant. When you take what's the slope of a constant? Yeah, the constant isn't changing, and the slope is all about change. Well, there's no change. There's no slope. Slope is 0. Okay, now you can't really see that, so I'm going to write them down. And I'm going to write them down in terms of t. This is so much paper. These are rules to follow. The most important rule is called the power rule. And if x is equal to some constant, I'll call it a, times t to some power of n. If you operate the derivative on it, now the derivative is that limiting process to this general expression, the mathematicians have graced us with the answer. Okay? Dx dt is equal to a times n times t to the n minus 1. Okay? Does that look kind of crazy? It's not crazy if you look at, like, let's do an example. X equals 4t to the 7th. Well, what is dx dt? Well, it's a times n. A is 4, n is 7. 4 times 7 is 28 times t to the n minus 1, 6. There's your answer. Okay, there is another mathematical expression. X is equal to e to the a times t. Anytime you see a in this, it's a constant. This is the exponential function. The exponential function is kind of cool. Dx dt is just going to be a times e to the at. The exponential function's derivative is itself. But then you have this constant. And those of you who've already taken calculus, where did this a come from? Chain rule. Okay. It's from the chain rule. All right. Sorry. And so, you'll learn about the chain rule in your calculus classes if you haven't. But for right now, just plug and chug. Just follow the rules. What if x is equal to the sine of a times x? Well, the derivative of a sine wave is a cosine wave. It's just going to be a. You need to keep that a comes in cosine a. Oh, wait, I meant to put t in there. I'm sorry. Okay, now, there's a whole bunch more of them on page 825 of your book. And if you don't want to do that, if you're watching this on the video, by the way, I will just magnify this and then freeze it. All right, I hope you can see that. These right here is all you need. Now, what you can do here is anywhere you see an x, just put a t for time, because everything we're going to do right now is time-based, and you can solve it. So it's just plugging and chugging, okay? No thought required except to follow the rules. Now, where these rules are derived, how they're derived, that's what you're going to do in your calculus classes. But I don't have time to teach a calculus class and an AP physics class. We use calculus in physics. So these are the rules you're going to need to know for differential calculus. But it all comes down to this. It all comes down to that the derivative is a function that describes the slope of another function. So just remember that, and then we're just going to use some mathematical tricks to figure out what this function is analytically. Okay, so I'm going to hand out the worksheet now, and that'll be your homework to work those problems. Hey, if you are new to calculus, I expect you to go under somebody's wing who has done this before and get help from them or get help from me. Perfectly legit to get help from people. All right? That is all.